What if the next war isn't fought by soldiers, but by machines that think for themselves? Welcome to the battlefield of tomorrow, where drones don't just fly. They decide who lives and who doesn't. In today's video, we're diving into the rise of sentient drones, autonomous war machines that could replace human fighters, change the rules of engagement, and blur the line between intelligence and instinct. This is not science fiction. It's already happening. Stay tuned, because what you're about to see might just redefine modern warfare forever. Using advanced natural metamaterials, scientists have engineered materials that bend light waves, drastically reducing both the thermal and visible signatures of a target. The science behind it is surprisingly straightforward, though skeptics like to joke, "I'll believe it when I don't see it." This form of adaptive camouflage creates the illusion of what's behind an object by bending light around it. The military implications of such developments are clear. An invisibility cloak would allow warfighters, from infantry to special forces, to operate deep inside enemy territory without being detected, or at the very least, long enough to seize the initiative. Such capabilities would not only reduce the risk of casualties during operations, but also increase the likelihood of successful surprise attacks, surgical strikes, sabotage missions, and assassinations. A Canadian company is reportedly said to have demonstrated this material to 2 command groups within the U.S. military and 2 within the Canadian Armed Forces, as well as to federal counterterrorism teams. Of course, if this technology were to fall into the hands of non-state actors, such as guerrilla forces or terrorist groups, it could pose serious challenges for military and homeland security operations. The electromagnetic railgun launcher uses magnetic fields instead of chemical propellants, such as gunpowder or fuel, to fire a projectile at extreme velocities, between 4,500 and 5,600 miles per hour. This emerging technology has demonstrated the capability to launch a projectile over 100 nautical miles using a 32 megajoule power source. The railgun's incredible speed and range offer major offensive and defensive advantages, from precision strikes capable of penetrating even the most advanced regional defense systems to missile defense against incoming aerial threats. Another key benefit of this technology is that it eliminates the need to store dangerous explosives or flammable materials required by conventional ammunition. The U.S. Navy's Office of Naval Research has been developing a ship-mounted railgun system since 2005. The current phase of the project, launched in 2012, focuses on demonstrating repeat fire capability or sustained firing rates. The Navy ultimately hopes to extend the weapon's range to 200 nautical miles using 64 megajoules of energy. However, since a single shot requires up to 6 million amps, a current stronger than that which powers the Northern Lights, it may take years before scientists can develop capacitors capable of delivering such power or create barrel materials strong enough to survive repeated firing without shattering. Not to be outdone, the U.S. Army has been developing its own ground-based electromagnetic gun. China is also rumored to be working on its own version, with satellite imagery from late 2010 showing possible testing at an armored artillery range near Baotou, Inner Mongolia. Despite international pressure to prevent the militarization of space, major powers continue to explore technologies that could turn the skies above us into the next battlefield. The possibilities are as limitless as they are strange, from lunar missile launch platforms to systems that could capture and redirect asteroids toward targets on Earth's surface. Of course, not all of these scenarios are technically feasible and may forever remain in the realm of science fiction. But several breakthroughs are well within reach of current science and could fundamentally reshape the nature of warfare as we know it. One real possibility is arming spacecraft with nuclear or non-nuclear electromagnetic pulse (EMP) weapons. By detonating an EMP device from a satellite at high altitude, a nation could launch a decapitation strike that disables an enemy's electrical grid, satellites, and the entire command, control, communications, computers, intelligence, surveillance, and reconnaissance C4ISR architecture needed for military operations. Depending on the size of the EMP device, the strike could cripple an entire country or be more surgical, targeting just one region of operations. A killer mace weapon of this kind could, in theory, end a war before a single shot is fired, especially against adversaries highly dependent on digital infrastructure, like the United States, far more so than, say, the Taliban or Hamas. EMP weapons launched from lower altitudes or land-based platforms, like ICBMs, are more vulnerable to interception or preemptive strike. By contrast, satellite-mounted EMPs would be out of reach for most nations, except those with advanced anti-satellite capabilities, either from ground-based systems, space interceptors, or armed spacecraft. Moreover, response time to a space-based blackout would be drastically shorter, making interception far less likely. Another long-studied technology is space-based high-energy lasers, SBLs, used to intercept ballistic missiles during their boost phase, a concept known as boost phase intercept, BPI. The advantage of BPI is that the missile is still moving relatively slowly during this phase, increasing the chance of a successful interception, unlike land or sea-based BPI systems, such as Aegis, that must be deployed close to enemy territory. Space-based laser platforms can operate at altitudes far beyond the reach of the target nation's defenses. As more nations, and potentially rogue states, gain access to long-range and possibly nuclear, ballistic missile capabilities, interest in SBL interceptors and funding for such costly programs will likely grow. Still, serious challenges remain in developing megawatt-class chemical lasers suitable for orbital deployment. Had hypersonic cruise missiles existed in the mid-1990s, the United States might have taken out al-Qaeda leader Osama bin Laden much earlier, possibly even in Afghanistan instead of Pakistan. With the ability to deliver precision warheads across long distances, cruise missiles have already had a profound impact on modern warfare. But in an era where minutes can mean the difference between failure and success, traditional cruise missiles can be too slow. When the U.S. launched a land attack cruise missile, LACM, from a Navy warship in the Arabian Sea in 1998, retaliating for al-Qaeda's embassy bombings in Kenya and Tanzania, it took 80 minutes to reach the terrorist training camps in Afghanistan. A Mach 5 plus hypersonic missile could have struck those same targets in just 12 minutes, short enough to act on time-sensitive intelligence and eliminate the terrorist mastermind before he vanished. This desire for global reach at near-instant speed led to the development of a program known as Prompt Global Strike, initiated by the U.S. military in 2001. Efforts centered around the X-51A Hypersonic Cruise Vehicle, HCV, a joint project between the U.S. Air Force, Boeing, DARPA, NASA, Pratt & Whitney Rocketdyne, and the Air Force Research Laboratory. Meanwhile, Russia, China, and India have also made significant strides in developing similar capabilities using conventional warheads, prompting concerns among defense analysts of an emerging global strike arms race. The U.S. Navy is currently exploring the possibility of launching hypersonic missiles from submarines. As the 1998 example illustrates, Prompt Global Strike could serve a wide range of missions, from decapitation strikes targeting heads of state, command and control centers, and other high-value targets, to surgical strikes on mobile terrorist groups during narrow windows of actionable field intelligence. Meanwhile, the sheer speed and terrain-skimming nature of hypersonic cruise missiles would pose serious challenges to existing air defense systems, giving them a major tactical edge in conventional warfare scenarios. Arguably, the most significant development in the defense industry over the past decade has been the rise of unmanned vehicles. As technology advances, drones, in all their forms, are rapidly taking over roles once exclusively held by humans. The progress has been so profound that some experts now suggest that manned combat aircraft could one day become obsolete. But today's drones, whether they're bomb disposal robots, mini submarines, ship-based surveillance helicopters, or airborne assassination platforms, are still far from truly autonomous. Most still require some level of human intervention. Many are remotely piloted, and key operational decisions, such as identifying a target or launching a Hellfire missile, still rely on human oversight. That reality, however, is beginning to shift. As scientists push the boundaries of artificial intelligence, The day may come when drones are capable of making life and death decisions independently, while drones, or robots more broadly, don't possess human-like intelligence or consciousness. Breakthroughs in computational power are giving machines greater situational awareness and the ability to adapt in real-time. As these systems evolve, we could see drones become true fire-and-forget weapons, capable of loitering over a target for hours, reacting with precision and speed once a kill opportunity presents itself. Their endurance and focus would vastly exceed that of a human soldier or pilot. And as the costs of recruiting, training, and retaining human troops continue to rise, not to mention the human toll and grieving families, the appeal of autonomous systems only grows. Allowing robots to make lethal decisions may seem like a dark leap forward, but in many ways, it's a logical extension of modern, gamified warfare. These machines create yet another layer of emotional distance between those who initiate violence and those who suffer from it, potentially lowering the psychological threshold for using force. Once militaries commit to using drones in combat roles, the next logical step will be maximizing their autonomy. In a future battlefield, the side that acts fastest, with the fewest human bottlenecks, will likely dominate. Thanks for watching. Subscribe for more videos.